All right. So I'd like to welcome all of you to Qiskit Forfeit Ghana version. You're all welcome from wherever you are joining us from. So we are saying a good morning, a good afternoon, a good evening to you all. We are excited about today and we're excited for your consistency and your patience throughout this workshop. As you already know, the theme for our workshop is quantum computing for social good. Yes, indeed, we've had some background, we've learned something, and we are saying after this workshop, what's next is to make an impact. So we are looking forward to the future where we could solve societal problems in Ghana here using quantum computing. For those of us in Africa, you realize that we have a lot of issues we could address. So from Lawrence talk yesterday, we looked at different aspects of application, optimization, energy, finance. So we are very fortunate to know that quantum computing can be applied in all spheres and every area of our life. So we are looking forward to that great future for us in Ghana, for Africa, and for the world. So we appreciate you, our participants who are here with us. Today is day 2, and we continue with our lecture series. But before then, like I promised yesterday, we'll have some time to get to know each other. We've been doing that so far from the chat room, but today we are good to go with some breakout rooms to get to know each other. So we'll have some few minutes to get to know each other. So when you get to the breakout room, you can introduce yourself, talk about your area of research and other things that might interest both of you or the members in the group. So let's get to know each other now as we break into our various rooms. Okay. Yeah, so let's join our breakout rooms. Yeah, so I guess we all had a very great session, getting to know each other. So if you enjoyed this session, kindly show a thumbs up in the chat box. You can share something with us in the chat box to see how excited you were, what you learned about your other partner as well. That's great.
Are
Wonderful.
120 தானுங்க 2 மசாலா ஒரு பேஜ்.
Okay, so I'd like to welcome you all once again to Qiskit for First Ghana Day 2. Our lecture continues today, and we are very fortunate and to have a very resource person, a very seasoned person. As at May, he had over 30 certification in quantum computing. So I am getting now, he may be having over 50, if I'm not exaggerating, over 50 certification in quantum computing. He is a lecturer at University of Energy and Natural Resources, Ghana, for our foreign participants. Yes. And he's a very active researcher in quantum computing. He has made some strides in quantum computing. He has been leading to build the quantum computing in Ghana as well. So it's good to have him with us today to take us through another basic aspect of quantum computing as well. And today is the day we get to do some lab work as well with him. So we'd like to welcome Dr. Peter Nimbe. Hello, Doc. So give Doctor some few minutes to unmute himself and join us. Dr. Nimbe. Okay, so Dr. Nimbe will be joining us soon. So as he prepares to join us, let's continue to make use of the chat room. You can share your experiences with us in the chat room. But then a few notes as he gets ready. It's aside we having the lab session today, we'll upload a lab as well on our GitHub, and that lab is for you to actually go through the lab. It's a graded lab. So we look forward that you download the lab and you could do it locally, run it locally, or using the IBM Quantum platform. But after going through the graded lab and which platform to use with Emmanuel Ofusu, we think that the best option would be to use the IBM Quantum platform. Ofusu, right? Yeah, so our best option is using the IBM Quantum platform to run your graded lab because we tried it locally and it didn't look friendly at all. It didn't look easy at all to actually run it locally and get everything. So, but it's more easier if you decide to do it on the IBM platform. With that, you don't get to as well install much packages because everything has already been embedded in it. So you get to receive that lab in your GitHub and work on it. So maybe I can just, since we are waiting for Dr. Nimbe, I can show you around. Hello, Dr. Nimbe. I'm not sure he's still here. Okay. Dr. Nimbe, please, are you ready? Okay, so let me share this lab with you now. So I'm going to share my screen. Hello, Dr. Nimbe. Okay, kindly give me some few seconds to share my screen with you. Okay, so I'm going to share a zip file with you. So this is the zip file. Please, I hope you can see my screen. If you can see, show a thumbs up. Just to be sure you can see my screen and you can see a folder. And in that folder, you have Qiskit's 4 first challenges. Okay, very good. So I will share a zip file with you titled Qiskit's 4 first challenges 2023. So when you receive this zip file, you download and unzip. When you unzip, you have the Qiskit's 4 first challenges. So this is it. I open, and when you open the folder, you notice that you have 3 labs there. That is lab A, lab B, and lab C. So these are the labs, the graded lab that we are supposed to solve. So I will send these labs to you and these images as well, the image folder as well. You need the image folder because when you are running, there are some images in the labs that is pulled from this images folder. So that will be shared as well. If you want to go through how to run the grader lab, you can look at this, the README in Word documents or PDF documents. You also have a very short video, which is to just a quick setup how you run the graded lab that you will be given. So if you are able to unzip and you have this, if you are facing problem running it locally, and like we are advising, you can do it on the IBM platform, then you can just share, you can go to, okay, so I want to just show you my lab. So, okay. So I hope we can all see the IBM platform, the IBM Quantum platform. So let me know if you can see that. Just give a thumbs up, just to know that you are following. Okay, very good. So we've already learned how to create our IBM platform. So I'm assuming by now we all have accounts here. So for me, if I open the platform, I sign in. So I sign in using my Google account. So let's sign in using my account. Okay, it's taking some time to respond. All right, so this is my platform. How do I run those lab exercises here? So I can go to, so if you open this, for those who are very familiar with it, I'm sure you have all seen this interface before, but for those who are new, you can come to, you scroll down where you have your quantum lab. So let's click on quantum lab. Okay, so the page is loaded for me. Okay. All right, so you realize that, okay, so these are exercises I have done so far. Okay, so what you can do is, because you have the zip file, you have unzipped, you can upload your lab files here so that you can run. So what you can do is you can first create a folder. So you realize you have this create new folder option. You have to create a new folder option. So we can quickly go through. Then Dr. Nimbe comes. Then when he's done, I think we can go through again as well. So you create a folder. So you see the button here, create new folder. So you click on that, then you create a folder. So let's say you want to call it Qiskit for first Ghana. So I'm just doing it. So enter, and you have created the folder. So this is the folder I have created. If I click on this folder, I can upload all my labs into this folder. So upload. So upload files. So you click on upload. It takes you to your computer. So wherever you have your files, you go to that place. So you realize that I have mine here. So I can select the lab I want to upload. So select all this lab there. Then you upload online. Okay, so you realize that the labs are uploaded in that folder that you created. But then you remember I didn't mention about the image folder. You need the images in that folder as well. So in this folder, I can create another folder again. So I'm still in the Qiskit for First GH that I created. So I can create another folder called images. Images. Okay. Then in this new folder, if I open this folder, this images folder, I can upload the images in the images folder that you have. So these are the images I have. So I'm selecting all my images here. Then I open and they all get uploaded. Voila. Hey, that's congratulations to me. I made it. So you have everything on the IBM Quantum Learning platform now. It will be easier for you to do your graded lab exercises. So I'll end here as Dr. Peter Nimbe is ready for today's lecture. After the lecture, we'll have some few minutes to go over again. Thank you so much. Dr. Nimbe.
Okay. Thank you very much, Dorcas. I hope I'm audible.
Very audible.
Okay. Let me share my screen.
All right.
I hope you can see my presentation.
Yes, please.
Okay. So we're going to do a quick overview of Qiskit before we jump straight into code. There are a lot of things we need to understand But before then, I'm Dr. Peter Nimbe, and I'm a lecturer in University of Energy and Natural Resources in Sunyani. I did my first degree in Calec University in the area of computer science. I had my master's degree in computer science in KNUST, and I had my PhD in computer science in University of Energy and Natural Resources. So I have skills in quantum computing, blockchain, cryptography, machine learning, and so on and so forth. The list goes on. And I have quite a significant number of certifications, probably over 40. So yeah, so let's begin. Let's take a look at what Qiskit is all about. So Qiskit is just an open source toolkit for useful quantum computing. And it is, if you want to engage in quantum computing, Qiskit is the way to go. There are other platforms that you can use, but that are by different organizations. For example, Google have their platform, IBM have their platform. Other companies, renowned companies and institutions internationally have their platforms that they can program and do their quantum computing course and all of that. But we are focusing on Qiskit, that is by IBM. So Qiskit has some certain libraries that we are going to make use of as we progress. It has a comprehensive set of libraries and gates that we are going to use to build circuits and to also write our simple programs here and there. So we can run your codes on any hardware that is usually available by means of the Qiskit platform. So once you have Qiskit, you don't need any serious resources in order to run Qiskit on your machine. With your classical computer, you can easily run your Qiskit and run your circuits and all of that. So we have some history of quantum computing that actually started all the way from the paradox and then all the way to the launch of the IBM Q experience. It all started in 1935, all the way into the Bell's inequality in 1964. The birth of quantum information theory began in 1970. Then we experienced quantum cryptography around 1984. Then we also looked at quantum error correction in 1995. Then we saw what is known as quantum teleportation in 1993 and down to 2016. And 2023, up to now, we are still using Qiskit. And Qiskit is one of the mostly used platforms for quantum computing in the world. Yeah. So that is how a simple quantum computer looks like, the IBM system. So I think Lauren talked about superposition, entanglement, and interference. So I'm not going to spend so much time. We know superposition is the ability of objects to be in multiple states at the same time. So in this case, we could have maybe qubits being in multiple states. So we could also have what is known as entanglement, which talks about the fact that there's a form of correlation between objects, even if they are separated by large or long distances. So no matter the distance of objects, there's some form of correlation between them. And that is what is known as entanglement. So if we can explore this property of entanglement, then we can do a lot of it with this property. So, conventional computers actually use zeros and ones, whilst quantum computers is more like a superposition and all of that. So the cat paradox, Schrödinger cat was explained yesterday, so I will not talk about it so much, looking at the fact that a cat could be dead or alive at the same time. That is a state of superposition, right? So let's jump straight to, let's take a look at what some of the differences between classical computers and quantum computing is all about. So, for quantum computers, we are looking at qubits. But when you look at classical computers, that is our conventional computers we are using currently, we are looking at 0 and 1 bit. So whereas classical computers are dealing with bits, we are looking at qubits for quantum computers. We also see that quantum computers have high error rates compared to classical computers, which have low error rates. So these are basically some differences between classical computing and quantum computing that we can take a look at. So we've explained what the classical bit is, 0 or 1, and the qubit is that. And usually qubits are surrounded by the bra and the ket notation. So you need to understand what the bra and the ket and all of those things is all about. We'll take a look at that shortly. So this is how qubits could be represented on the Bloch sphere. And we'll look at what the Bloch sphere is and how to actually program it and all of that. So it's just a circular ball that shows the state of a particular qubit at any point in time, or the state of an object at any point in time, depending on the gates that we apply. So we have so many gates when it comes to classical computing, and we have so many gates when it comes to quantum computing. I'm sure most of you have heard of the AND gate, the OR gate, the NOT gate, the XOR gate, and so on and so forth. We'll take a look at it briefly so that you'll get to understand what this gate is all about before we dive into quantum gates. So that is it. Let me just move straight to the classical gates, then we can move on to the quantum gate. You have access to this slide, so don't worry about that. Okay, let's take a look at classical gates. Now, you've also heard about truth table and all of that. So in somewhere in mathematics, you know, it's a combination of on or off values, or a combination of 1 or 0 values that is resulting in an output. So if you take let's look at the logic gate. So logic gate is a device that acts as a building block for digital circuits. So anytime you want to deal with digital circuits, you have to look at logic gates. And logic gates are the same as classical gates. So the basic gates we have are the NOT, the AND, and the OR. I'm sure most of you have heard of the NOT, the AND, and the OR gates. All right, so the OR gate, if I have an off and an off, it's an off. So let's assume that the off is 0 and the on is 1. So 0, 0 is 0, 0, 1 is 1, 1, 0 is 1, and 1, 1 is 1. So whether you are using on and off values, or whether you are using 1 and 0, we should be able to get the required output. So for the AND gate, we have off, off is off, off, on is off, on, off is off, and on is on. That is the AND for you. So for the on, even if we have one of them being off, it is automatically off. So all right. So now, as I said, for OR, 0, 0 is 0, 0, 1 is 1, 1, 0 is 1, and 1, 1 is 1. For AND, 0, 0 is 0, 0, 1 is 0, 1, 0 is 0, 1, 1 is 1. So that is what it's all about. And this is the symbol for the OR gate, and that's the symbol down there for the AND gate. So I'm sure most of you are already familiar with this. The inventor of the idea of logic gates is George Boole. So you can read more about this guy who came or invented this logic gates and all of that. So read more about him. Yeah. So let's take a look at the XOR gate. Yeah. For NOT gate is very, very simple. So if it's not a 0, it is 1. If it's not a 1, it is 0. So that is how the NOT gate operates. So if I can add a NOT gate to an AND gate to form a NAND gate, so, and I can add a NOT gate to the OR gate to form a NOR gate. So there could be a combination of these gates that you could actually put together to get certain outputs and so on and so forth. So that is how logic gates it works. So you see at this point in time, we have and we have 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. But then if you look at the NAND gate, because of the NOT gate that has been attached to it, it is the complete opposite of it. So all the zeros will now turn to 1, and where we had 1 will become 0. So that is the output we are having over here. The same applies to the NOR gate. We just invert this OR gate. Wherever we have zeros, we replace with 1, and wherever we have 1s, we replace with zeros. So very, very simple. Logic gates for classical computers. You don't have to actually do a lot of thinking in here. So that is it. The last gate is the XOR gate. And for XOR, as if you have a 1, one of the inputs being a 1, we automatically get a 1. But if both of them are 0 or both of them are 1, is 0. So that is how the XOR gate works. You can also apply the NOT gate to the XOR gate and then invert this whole output. So if I apply the NOT gate to XOR, it means I'm going to get the XNOR gate. And the XNOR gate, it means 0, 0 will give me a 1, 0, 1 will give me a 0, 1, 0 will give me a 0, and 1, 1 will give me a 1. That is how the XNOR gate will operate. So that is what we are having here. We have the basic gates, and we have the NOT gate applied to the basic gates to get this particular gates that we are seeing here. So it's just the opposite. The NAND gate is just the opposite of the AND gate. NOR gate is just the opposite of the OR gate. The XNOR gate is just the opposite of the XOR gate. Very, very simple and easy to understand. So this is just a simple circuit in classical computing. I'm sure most of you have seen this over and over again. Yeah. Let's move to quantum gates. Yeah. So now that we have an idea as to what classical gates are, the AND, the NOT, the XOR, and so on and so forth, we can also take a look at quantum gates. Today we'll just take a look at the Pauli gates, and then we'll look at the Hadamard gate. And if there's more time, we'll take a look at the CNOT gate. So, but before that, let's do some project this. Let's do. So you want to know the gates that is used in quantum computer. We have the Pauli S gate. We have the Pauli Y gate. We have the Pauli Z gate. We have the Hadamard gate. We have the phase gate. We have the T gate. We have the control NOT gate. We have the swap gate. We have the Toffoli gate, and so on and so forth. These are examples of gates you can use in quantum computing. So we're going to experiment. We're going to play around with some of these gates in order to actually see how it functions and all of that. So you must understand that a classical bit is actually a binary unit of information used in a classical computer, but a quantum bit is the fundamental unit that is used in quantum computing. So you have to understand that in that perspective. So before we progress, I just want us to, if there are any questions, kindly ask them before I dive deeper into the quantum gates and what it's all about. Any questions so far?
Yeah,
If
so
everything
you
is
have
okay.
a question. You have a question. It says that classical gates are made up of transistors. What are quantum gates made of?
Oh, okay. So quantum gates actually have different materials that could be used. We don't have a specific material. For example, we have superconducting qubits or quantum computers. We have ion-trapped quantum computers that are being explored by different organizations. So the way we have classical computing, we have a standard where transistors are being used. For quantum gates, there is not one particular standard as of now. Different institutions are using different technology in implementing their quantum gates, but generically, we are looking at electrons or photons. So if you understand the concepts of electrons and photons, then we can proceed from there. But if you are referring to the technology that is being used, different organizations are using different technology right now, and there's not really a standard. But the standard is that we are all dealing with electrons, we are all dealing with photons, we are dealing with electrons spin up and spin down here and there. So the basic idea is the same across all quantum computing platforms, but then the technology behind might differ from organization to organization, because the way the IBM quantum computer is set up will be different from the way another institution like maybe the Google, their quantum computer will be set up. And the materials and the tools they use and the approach they use is kind of different. But fundamentally, they are all dealing with photons, they are all dealing with electrons, and they are all dealing with qubits. So that is the fundamental thing that is at play. I don't know if I've answered him.
Yes, you have.
Okay. So on this note, I'm going to actually share, use the whiteboard. I tried getting a light pen. I could not get one here in Sunyani, so it means I'm going to use my hand. The whiteboard, you know, where do I locate that? Let me just use the paint. If I'm not seeing the whiteboard, maybe I'll just use the paint.
To use a whiteboard, you may have to stop sharing and share the whiteboard.
Oh, okay. I see. All right. Then let me do that. Whiteboard. I think the whiteboard is taking quite some time to load. Okay, so let's take a look at some few things. I'm sure you guys have heard of qubits, quantum bits. No, qubit is just a short version of a quantum bit, and usually, when you want to represent a qubit, you use what is known as the Dirac notation, and this Dirac notation was introduced by Paul Dirac. And then, so if I have something like this, it is 1 qubit. If I have something like this, it is a 0 qubit. So you have to take note of that. Now we have to distinguish between what is known as the bra and the ket. So usually the Dirac notation is used to describe the value of a qubit as a vector in the sphere. So you have to note that this is an example of a sphere. So for this sphere, we could have a 0 at the top and we could have a 1 at the down. So that is how the Bloch sphere actually looks like. I'm not using a light pen, I'm using my finger, so bear with me. So it is just a rectangle, a circular, a circle that has a 0 on top and 1 down there, which are the poles of the sphere. So now, so that is 1 qubit and that's 0 qubit. So anytime you want to represent 1 qubit and 0 qubit, that is how it is done. You just have to use the Dirac notations to do that, and then you'll be fine. Now, if I have, let me get an eraser. Where's my eraser? How is this eraser? I'm not familiar with the whiteboard here. I think let me just use paint. I'm familiar with paint. I'm not familiar with this whiteboard. Not even seeing the eraser. Okay. Let me use the paint. Okay, I hope you can see the paint. So, as I said, if I have a circle, on top of this, I have a 0. Down here, I have a 1. So, I can have an arrow pointing downwards to this 1, which is down there. And this is a spin down state. This is called spin down. Alternatively, if I have a circle and I have the arrow or the direction pointed to the 0 qubit, then I have what is known as a spin up state. So take note between the difference between spin down and spin up. So when the direction is pointed towards the 1 qubit, it's called a spin down. When the direction is pointed to the 0 qubit, it is called a spin up. Now, the 0 notation, as in the 0 qubit, is the same as the vector 1, 0. So anytime you see the 0 qubit can be represented as a vector and vector. So we have 1, 0 represented 0 qubit. If I want to represent the 1 qubit is represented as a vector 0, 1. So always take note of this when you're using it in your computations and all of that. 0 qubit is equivalent to 1, 0 vector. The 1 qubit is equivalent to 0, 1 vector. Kindly take note of that. Very, very important. Now I asked somebody will asking why we are using vectors and matrices in quantum computing. It's very, very important because usually we must also take a look at what is known as scalars and vectors. Scalar quantity is always dealing with magnitude, but a vector quantity actually deals with both magnitude and direction. And if you are dealing with quantum computing, you are dealing with the spin of electrons, that is a spin down and a spin up, and you're dealing with various rotations and transformations. You have to understand that because the arrow is always pointing at a particular place, there is a direction. So that is how come we have to use vector quantities, because vector quantities have magnitude and direction. If we had represented qubits with just scalars, it won't work because we are looking at magnitude and direction, and scalars only deal with magnitude. So you have to understand that I'm sure you know a lot about vector quantity and scalar quantity. In vector quantity, we are talking about displacement, velocity, and so on and so forth. When we are talking about scalar, we are looking at the length, area, volume. All of these are scalar quantities. So you have to take note of the difference between the scalar and the vector quantity. It's very, very, very important. So now that we understand the vector representations of each of the qubits, and we understand what spin down and spin up is all about, I think we can progress from here. So as I've said, there are various platforms that we can use, but then we are dealing with Qiskit. So that is where our focus is. You could have used platforms like SEC, TensorFlow, Quantum, Microsoft Quantum Development Kit, and all of that. But Qiskit is the most used quantum computing platform in the world by international business machines. So now let's take a look at some elements of Qiskit. Now Qiskit has basically 4 foundational elements. We have the Qiskit Aer, we have the Qiskit Ignis. Let me just create a new file. So we have the Qiskit Aer, we have the Qiskit Aer, we have the Qiskit Ignis, and we have the Qiskit Aqua. So these are the 4 foundational elements in Qiskit. So for our purposes, we might be using AER most. For Terra, Ignis, and Aqua, will not be using them. Ignis is basically for quantum error correction. So if you are someone who is into error correction or noise, that is correction of errors or noise, then you look at Ignis. But for AER, we're basically looking at accelerating development via simulators. So AER is something of interest to us that we'll be using very, very frequently. For Aqua, we are looking at building algorithms and applications. So if you want to build algorithms, you want to build applications, then Aqua is the place for you to go. So Aqua is basically for algorithms and applications. Ignis is for error correction. AER is for accelerating development using quantum simulators and all of that. So for us, our focus will be on AER. Yeah. So these are the 4 foundational elements of Qiskit that you have to understand. Very, very important. Now let's look at the Pauli S gate. Now the Pauli S gate, I'm sure most of you have heard Pauli S gate. It's one of the quantum gates in quantum computing. So you have to understand that just like we have classical computers, we're using AND or NOT and so on and so forth. Quantum gates, in order to actually do anything in quantum computing, you have to explore the gate. Without a gate, it becomes very difficult for you to actually do anything in quantum computing. So let's look at the Pauli S gate. I have explained what the 0 vector is. That is 1, 0. And the 1 vector is, which is 0, 1. That is very, very clear. So, and I said 1, 0 is spin up and 0, 1 is spin down. So you have to take note of that as we move ahead, because we are going to do some mathematical computations very soon. So try to understand. It's very, very simple. It's not complex. Very, very easy to understand. All right. So Pauli X. So now Pauli S gate can be represented by a Pauli X matrix, and that matrix is 0, 1, 1, 0. So that is the Pauli matrix, Pauli X matrix. So it's represented by 0, 1, 1, 0. I'm sure most of you are aware of matrices, so shouldn't have any big challenges from here. Now let's assume that we are in a 0 state. in the Bloch sphere, and we want to apply the Pauli X gate to the zero state. It means that Pauli S gate must give us a particular output. Now, for classical computing, you've heard of the NOT gate, right? So the equivalent of NOT gate in quantum computing is known as the Pauli S gate. The Pauli S gate. So if you want to invert anything in quantum computing, normally use the Pauli S gate. So if it's classical computers, we call it the NOT gate. If it's quantum computers, we call it the Pauli S gate. So kindly take note, the equivalence of NOT gate in quantum computing is known as the Pauli S gate. All right. So let's see how we can transform, as we have an initial state of 0, and want to transform that state to a 1. How can we do that? We can only do that by using the Pauli S gate. So we just apply the Pauli S gate to the 0 qubit, and then we get a 1 qubit. That's very, very simple to do. So as I said, the Pauli S matrix is represented by 0, 1, 1, 0. Kindly take note of this as we progress. All right. Now, how do I apply Pauli X matrix? Assuming I have 0, 1, 1, 0, I said I want to apply it to the 0 qubit. Now, 0 qubit is the same as what? 1, 0. Right? 0 qubit is 1, 0. So if I want to apply the Pauli S gate to this, how do I compute the matrix, these two matrices? Remember that I said that you can apply a gate to a qubit in order to get a particular output. So at this point in time, we have the Pauli X matrix multiplying the 0 qubit. This is the 0 qubit, and this is the Pauli X matrix. We are multiplying the matrix representation of the Pauli X matrix by the 0 qubit. And what are we going to get? I hope you remember how to compute your matrices. You have 0 times 1, all right, plus 0 times 1 plus 1 times 0. Very, very simple. Then we have this 1 times 1 plus 0 times 0. I'm sure most of you are familiar with this. And when you compute this, you're going to get 0, because 0 plus 0, which is 0, 1 plus 0, which is 1. So you get 0, 1. And remember, I said 0, 1 is the same as what? 1 qubit. So you see, we started with a 0 qubit. We've transformed it all the way to a 1 qubit. And we did that using the Pauli S gate. So if I have a qubit and I just want to get the opposite of that qubit, as I have a 0 qubit and I want to get a 1 qubit, or I want to invert it, all I need to do is just to apply the Pauli S gate to it. And I get, so if I apply the Pauli S gate to a 1 qubit, assuming that this was not 1, 0, but it was rather 0, 1. So we have 1 qubit, and I want to transform it to the 0 qubit. I still have to go through the same process, and I'll end up getting, at this point, I'm going to get, so let's look at how that will look like. 0, 1, 1, 0. If I'm applying it to a 1 qubit, 1 qubit is what? 0, 1. So you do your computations, you arrive at, so we have the 0 qubit here, we have the 1 qubit here. So when you do your computations, you still get your 0 qubit. Very, very simple to understand. I hope I'm not confusing anybody. I hope it is clear now. Is there any questions before I progress? If you understand, just raise up your thumb to show that you understand so that I can progress. Are we good to go? All right. I think we can progress. So let's take a look at how we can program the poly S gate. But before we do that, we write any codes or anything. I think I'll just take a look at the poly Y gate, the poly Z gates, and then the Hadamard gate before I begin doing anything coding, so that I don't come back to this particular thing to do any mathematical stuff. So let me just finish up on the gates so that we can actually progress from there. Now, the poly Y gate. So we just looked at the poly S gate. The poly Y gate is also another gate that is used in quantum computing. The poly Y gate actually is represented by the matrix 0, negative I. So we have 0, negative I 0 as the matrix representation of the poly Y gate. Very, very important you take note of this matrix. So just as we are transforming the 0 qubit to a 1 qubit and the 1 qubit to a 0 qubit using the poly S gate, you can also do the same for poly Y gate, where we can have various transformations here and there. So for example, I can decide that I want to apply the poly Y gate to maybe a 0 qubit. If it's a 0 qubit, it means we have 1 0, right? So how do I compute this? So I have 0 times 1 plus negative I times 0, right? Then I have I times 1 plus 0 times 1. So when you do this computation, you end up getting 0 plus negative, you get 0 here, and I plus this, you get I. So you get 0I as your matrix, and 0I is the same as this. So that is how we use the poly Y gate. Now you have to note the difference between the poly S gate and the poly Y gate. The poly Y gate also operates just the same way like the poly S gate. The only difference is that the poly S gate, the poly Y gate actually operates on a Y-axis, and it uses an imaginary output rotating about the Y-axis. So that is the only difference between the poly S gate and the poly Y gate. So we are not dealing with imaginary axis when we are dealing with the poly S gate, but when it comes to the poly Y gate, we are dealing with the imaginary axis. That is how come you are seeing this. I is the imaginary axis. So, but basically they operate the same way. So there's no much difference between the poly S gate and the poly Y gate, only that their mode of operation differs when it comes to the usage of imaginary axis and all of that. So that is the Y gate. The Y gate flips 0 to the Y gate. If I have a 0 qubit, I flip it an I one, a 1 qubit with an I in front of it. All right. Let me go to a new sheet. So I have this. So poly S gate flips 0 to I1. That is very, very easy. And it flips a 1 to a negative I0. That is what the poly S gate does. But remember, when we're talking about the poly Y gate, when we're talking about the poly S gate, it only flips 0 to 1 and 1 to 0. Remember, poly S gate, we are looking at 0 to 1 and 1 to 0. But poly Y gate is still 1 and 0 we are dealing with, but this time around we are having an imaginary axis in front of it. So that is what differs between the poly Y gates and the poly S gates. All right. Now, let's take a look at the poly Z gate or the poly Z gate. Now, the poly Z gate is represented by the matrix 1, 0, 0, -1. So all of these are just matrices. It's just a play of matrices and vectors that we're actually dealing with. So we realize that this is the poly Z gate and 0, 1, 1, 0. This was the poly S gate matrix we used. And this is that of the Z gate. We also looked not too long ago that of the Y gate. So you just have to, if you note these matrices, you can do anything you want to do. So it's just a matter of multiplying the matrices by your vectors, and the vectors are actually qubits. So you just multiply your matrix and your vectors, and you get a particular desired output, and so on and so forth. So that is the poly X gate, the poly Y gate, the poly Z gate. That is how it operates. It's very, very simple to use. It's not anything of a big deal. So that is it. Let's look at the Hadamard gate. Anyway, I hope there are no questions, or is there any clarification one want to see before I move to the last gate, which is the Hadamard gate. Then we switch to some coding here and there. Any question so far? Do I have any question?
Sir, I have a question here. Like flipping on the y-axis, flipping on the imaginary axis. How do we physically imagine that, like interpret that?
Can you come again?
Okay, so the poly y gate, it flips on the imaginary axis, right?
Yeah.
So what does that physically imply? Like how can I imagine that?
Okay, so I think some of these things, you maybe when we start to program and you see how the qubits are navigating around the Bloch sphere, then you get to understand some of these things properly. Maybe when it's in a mathematical way like this, you will not really visualize it well until we begin to program and to see how the various transformation of the states takes place within the Bloch sphere. Then you get to understand how the movement goes like. So some of these things, you really visualize it when we are using the Bloch sphere to see it. But as I said, basically the poly S and Y gates are almost the same. They do the same thing, only that one is using an imaginary axis and the other is just a direct flip and all. But the movements on the Bloch sphere is different when we view it from the Bloch sphere. So it's all about the movements within the Bloch sphere. So I'm sure when we do some little coding and programming here and there, you'll probably understand this much better.
So thank you.
Yeah. So let's look at the Hadamard gate. The Hadamard gate. Yeah. So we also have the Hadamard. The Hadamard gate. I hope you can see Hadamard. Yeah. So the Hadamard gate is, we talked about superposition, objects being in multiple states at the same time and all of that. The gate that is used to represent superposition is known as the Hadamard gate. So if you want to represent something as superpositional state, then you have to make use of the Hadamard gate. That is the only gate that is used for superposition, right? The Hadamard gate. If you want to look at the C0 gate, C0 gate is basically used for entanglement. Remember the properties of quantum mechanics. We talked about superposition, we talked about entanglement. So if you want to place something in a superposition, we use the Hadamard gate. If you want to place something, you want to entangle two qubits, then you have to use the C0 gate. Very, very important. So let's take a look at the Hadamard gate. Now, the Hadamard gate, as I said, is used for superposition and all of that. Assuming I have a 0 qubit here, 1 qubit here, and we have the arrow pointing over here. Then have another qubit here. I have a 1 qubit here, and have an arrow pointing here. We differentiated between the spin up and the spin down states of the various electrons. So we have to understand one fundamental thing, that if you are placing something in a superpositional state, then it is more like something like in between 0 and 1. You can't really tell the state of that object at that point in time. That object can be in a 0 and a 1 state at the same time until it is measured. It is when it is measured that the state or that superpositional state collapses. So anything that is in a superpositional state, as soon as we measure it, it collapses. It collapses. That superpositional state collapses, and we now have what is known as the classical state. So that is something that I have to make clear before I proceed. We can put something in a superposition, but as soon as we measure it, it's no longer in a superposition again. That's now resulted in a classical state due to the collapse of the superpositional state. So very, very key and very, very important. Now, if I have for Hadamard gate, I can represent it by this matrix over here. That is how we represent the Hadamard gate, just as we have matrices representing for the poly S gate, the poly Y gate, the poly Z gates. We also have representation for the Hadamard gate, and that is what we have. So anytime you can easily apply a Hadamard gate to a 0 qubit, a 1 qubit, and all of that, and that transforms into some desired output that we want actually. So usually if I have a 0 state and I apply the Hadamard gate, I should get a plus state. And if I have a 1 state and I apply the Hadamard gate, I should get a negative state. All right. So let's say I have a 0 state. If I want to apply the Hadamard gate to this 0 state, I'm going to get a plus state as the resultant output. But then if it was a 1 state, as applying the Hadamard gate to a 1 state, I'm going to get a negative or a minus state. So if I have the Bloch sphere, you have a plus state looking something like this. That is how the plus state looks like. And then the negative state is looking something like this in the opposite direction. So that is this is the plus state, and this is the negative state. So if you apply the Hadamard gate to a 0 qubit, you get a plus state. If you apply it to a 1 qubit, you get a negative state. So the plus state is indicated by the direction which I've indicated over here, and the negative state is represented by the direction that I've also indicated here. So Hadamard is basically used to represent something in the superpositional state, and that is what the Hadamard gate actually does. So it's just to transform qubits into some kind of superposition and all of that. So that is what the Hadamard gate is all about. And we'll look at various codes you can use. This is more of a mathematical stuff we are looking at now, but there's a way we can represent the Hadamard gate, the poly S gate, the poly Y gate, the poly Z gate. We can do that in Python. and actually do some coding here and there in the IBM Q Experience platform. That's the Quantum Lab. You go there and do some small codings here and there. I think that one is much simpler compared to this mathematical stuff, but you need to understand and appreciate the mathematical perspective before you even delve into the programming part, because you are programming, but you need to understand the maths behind it, and that is very, very crucial. So let's take a look at the C0 gate. C0 gate. So the C0 gate is one gate that usually require two how do I call it? Let me call it parameters in this case. So it requires two parameters or two inputs. So usually need 2 qubits in here. So the first qubit, and the second qubit is what you supply to this C0 gate. Usually, one of the qubits is the control qubit, and the other is the target qubit. So C0 gate accepts 2 qubits or 2 parameters. One of them is a control qubit, and the other one is a target qubit. So you can have something like this. If I have this diagram here, this is how the C0 gate looks like. So in this case, the control qubit is 0 and the target qubit is 1. So that is how a C0 gate look like. So it is very, very important you understand how this C0 gate operates and all of that. I think when we start drawing the circuits and using some codes here and there, you picture this more clearly. So C0 gate accepts 2 parameters. One is a control qubit and the other is a target qubit. Because you are trying to entangle objects. You can't entangle one object. You can only entangle 2 objects or more. So that is basically why it is accepting two parameters. So it's just like saying that an object, I want to entangle myself. I can't entangle myself. I'll need another object in order to entangle. So that is how the C0 gate is. You want to entangle 2 qubits to form some form of correlation between the two of them. Then you need a control qubit and you need a target qubit in order to achieve this. Very, very important. So usually you see that we're going to use something like .cx in our Python programming, and say maybe something like 0, 1, which means that one is a control, one is a target qubit, and all of that. We're going to take a look at some simple codes very shortly. Yeah, so let's dive straight into our code and let's do some small coding here and there. So let me move to my IBM Q. Quantum Lab. So as you are supposed to actually present as your first assignment the lab A, which is the first steps. But I want to just show you how the poly S gate works and all of that. You can equally apply other gates to see how things are visualized. So initially, we need to import the various libraries that are needed in order to start using the quantum circuit and the gates and all of that. So the basic library that you use is Qiskit. So from Qiskit, import all. So you just want to import all libraries. You can actually import individual libraries. Yeah. like this, so that after importing the quantum circuit, you use the circuit. But then I prefer to just import everything so that I don't need to come back here every time trying to import something if in case I've left it behind. So you just say from Qiskit import all and be on the safe side. But then you could also call the quantum circuit object and it still works. So you realize that we have something like QC equals quantum circuit. So we are creating an object. This QC is more like an object or variable of this quantum circuit. So creating an object QC, and this circuit that we are creating, actually we are providing it with one input. So remember that this circuit can actually take two parameters as well. So we could have a situation where we just have one parameter, or we could have a situation where we have two parameters. If it's one parameter, it means we are just specifying the number of qubits. But if I specify another parameter like this, it means I'm talking about one qubit and one classical bit. So the second parameter is actually looking at the classical bits, and the first parameter is looking at the quantum gate. All right. So it depends on what you're trying to do. So usually you employ the classical bits if you want to perform a measurement. But if you are not going to do any measurement and you just want to visualize how this gate works, then there's no need to bring in the classical bits. So I create an object QC of this quantum circuit object. And after creating it, I gave it a parameter of 1 qubit. So we now pick this object, which is QC, and then we apply the poly S gate. So that is how to apply a poly S gate. You just set dot X and you supply the qubit you are dealing with. So back to my paint. If I have dot X and I say this, I'm applying the poly S gate to qubit 0. That is basically what I'm saying. So I can have QC dot X for poly S gate. If I was dealing with the poly Y gate, it would have been QC dot Y. Is the poly Z gate, it would have been QC dot Z. If it's a Hadamard gate, QC dot H. So very, very simple in applying the various gates in your code here and there. So let's go back to our. So after you've actually specified your circuit, supplying it a number of qubits and all of that, you applied the poly S gate. Then you will now draw your circuit. So using the draw method of functionality. So when you draw, this is what you're going to get. You will see something very simple and basic like this. So you just need some 3 lines of code in order to display this simple gate we have there, known as the poly S gate. Now you can visualize this in different ways if you want to. You can. So let's go down. Now, if I want to actually display this thing on a Bloch sphere, all right, what I can do is usually when you start a qubit, or when you start building a circuit, it's at the ground state. So by default, it is at the 0 state. So if I can decide to plot the Bloch sphere using these 3 lines of code I have here. Now, the first line of code basically is just to get our back end, because we've created a circuit, but we need to run the circuit on a particular back end. So we need to get the back end, and that back end can be gotten using the AER simulator. Remember that I said Qiskit is built on 4 foundational elements: the Terra, the AER, the Ignis, and so on and so forth. So The AER, we said, is for simulations and all of that. So if you want to accelerate simulations and all, use the AER. Since we are trying to do some simulation here, we use the AER dot get backend method. So that is how we can get our backend. So after getting our backend, we need to execute our circuit on that backend. So this code you are seeing here is basically executing our circuit on the backend. So that is how you do that. Execute, accepting two parameters. That is the circuit object, which is QC, comma, and the backend that we are trying to run the circuit on. So when we execute the circuit on the backend, we get a particular result. So that is what is meant by dot result. Now, after getting the result, we want to convert it to a state vector. Because if you don't convert it to a state vector, you cannot plot the Bloch sphere. That is how this whole Qiskit platform has been set up. So before you can actually display the Bloch sphere, whatever circuit you run on the back end, that result must be converted into a state vector. And that state vector supplied to the plot block multi-vector function. And then when executed, it results in this Bloch sphere you are seeing. So remember I said initially, when you run a circuit, it's in the 0 state. But because we apply the poly S gate flips 0 state to 1 state. So you see that we have the 1 state down here. So that is how the poly S gate operates. Very, very simple. Let's assume that we let's apply the poly Y gate and see how that also. So this is a poly Y gate. The poly Y gate. So remember, I said the S gate and the Y gate does the same thing, only that one is using an imaginary axis and the other one is basically just doing a flip. So you see something like this X, assuming the arrow came to this direction and it pointed somewhere here, that is a plus state. This is a state of superposition. This particular state where X is, that is a state of superposition, it's a plus state. If it was pointing in this direction, then we will be looking at something like a minus state, also in a state of superposition. So that is how we can use the X and the Y gates. Very, very simple. Now, if I want to visualize this whole thing in the form of a transition, then I use the visualize underscore transition functionality, where I just supply the circuit to it. So all I need to do is supply the circuit as a parameter, the circuit object, to the visualize underscore transition function. And this, when you run this, it will display this Bloch sphere you are seeing here. So you can actually view this Bloch sphere as a form of an animation. It will be moving slowly in a transitional state for you to see how it is actually operating. So you see, initially we had our ground state to be 0. Let's see how we can, if I can make this bigger. Let's see how this transition works. Anyway, so let's see. So you see, it was in 0 state, but it flips and comes to the 1 state. So notice the movements of the arrow. It is moving along the y-axis with the imaginary axis. So you have to take note. Remember, the code we have there is still the Y gate, the poly Y gate. So look at the movement of this from a 0 qubit to a 1 qubit, and it's moving in a particular axis. Let's assume that we're dealing with the S gate, and we run this. One gate flips it to 1, so look at the movement. Let's visualize this as well. Taking some time to do the visualization. Okay, so we are initially at the 0 state. Let's see how this is going to run. So for the S gate, this is how the movement is like. So we can visualize using the Bloch sphere. So Bloch sphere is basically used for visualization of how qubits can be transformed from one state to the other and all of that. So if you want to look at the visualization and the transformation of states, we just do that visualization on the Bloch sphere, and you can do it in a loop fashion and all of that. However you want to specify that, you can do that. So after doing the visualization, if you want to display a graph or a histogram, then you can use what is known as the plot histogram function. Before we can use the plot histogram function, remember that we started off by creating a circuit, and then the circuit object, we applied the S gate. After applying the S gate, we drew the circuit. After drawing the circuit, we try to get the back end so that we can execute our circuit on that back end, get the results, and then get a corresponding state vector in order to supply it as an input to the plot block multivector function so that we can actually display our Bloch sphere. Now, in order to visualize the Bloch sphere and its movements and everything, we use a visualize underscore transition function which accepted the circuit. Then from there, we want to display a histogram of our counts and results and all of that. So we have.
There is a question for you.
Okay, so let me just finish this and take the question.
All right.
Yeah. So I want to plot a histogram. Now, to plot a histogram, remember that I executed the circuit on a backend. That is that simple code you are seeing here. An execute function which has a QC object and a backend. So we execute that circuit. After executing it, the result is gotten, and we place it inside a variable or object called result. And now this result, we can apply a function called .getCounts to it so that it counts the number of, we're looking at probability and all of that. So there have to be some kind of count in order to determine the probability. So the result .getCounts, then the count is made and placed inside a variable object called the counts. Now this variable is then supplied to the plot histogram function. And when you execute this code, it displays this histogram that you are seeing. So you see we have a probability at your left, which is, and we have the 1 down here. So it means that 1 has 100% probability of occurring. That is because we are dealing with a poly S gate. So if I have a 0, that is a ground state, and I apply the poly S gate to the 0 qubit, I get a 1 qubit. So tells me that my 1 qubit has a 100% probability of occurring. That is when you apply the poly S gate to a 0 state in order to get a 1 state. So this is how we can visualize the the number of counts when it comes to the poly S-gate. Very, very simple to understand. Okay, so let me take the question now.
So we have the question in the chat. It says, please, in the first part of the code, where you initialize the poly gates, should the qubits always be 0, or it can be the 1 qubit as well?
Okay, all right. So it is not every time it has to be 0 qubits. You can apply the poly S-gate to any number of qubits that you want. For example, let's assume that my quantum circuit has 2 qubits. So you see, I have 0, 1. Initially, we only had 1 qubit, but because I specified 2 here, and I have 2 qubits over here. Now, this S-gate means I'm applying the poly S-gate to the 0 qubit as it stands now. If I apply the poly S-gate to the 1 qubit, all I need to do is just change this to 1, and then it does that for me. So you can apply the poly S-gate, the poly Y-gate, the poly Z-gate to any qubit you want to apply to. It might not necessarily be the 0 qubit. Yeah, I don't know if I've answered the person. Okay, so that is how we can apply the poly S-gate, the poly Y-gate, the poly Z-gate. It's just something simple and basic. It's not really anything difficult. Just trying to create a circuit, applying the gate and drawing the circuit, and doing some display of the Bloch sphere here and there. So you can equally display various kinds of circuit. This is just a circuit with 2 qubits. I can decide to even create a circuit with 2 qubits and 2 classical bits. So you realize that when I run this program, you see 2 classical. So you see, initially, if you didn't have this down here, because I created 2 classical bits, these 2 classical bits has been created. What am I going to use this classical bits for? I'm going to perform some measurements on these qubits. And even when I perform the measurements, it has to be in a classical state, because as soon as the superpositional state collapses, we are looking at actually a classical state. So that is where you actually use the classical bits. So if not, you will not really use them. You can stick with your quantum gates if you are just doing some basic stuff here and there. Yeah. So I don't know if there's any more questions. Is there any more questions? Okay, so basically, we can also do this after creating 2 circuits, 2 qubits and 2 classical bits. We can also do this, assuming we want to perform some form of measurement. We can do that. So let's see how we can perform the measurement. So qc.measure, all right. Now I want to measure my qubits, so I have to measure it, and it's going to result in a classical bit. So performing the measurements, I have something like this. So I can have 0, 1, 0, 1. So because we are dealing with 2 qubits, so we have the first qubit, the second qubit. We also deal with 2 classical bits, which is obviously 0 and 1. So if it was 3 qubits and 3 classical bits, then this would have been 0, 1, 2. This would have been 0, 1, 2. So we can perform measurements and stuff here and there. So you see, when you perform the measurement, you realize that all the qubits are measured. You see some measurement images appearing, which shows that the Q0, Q1, Q2 are being measured, and they are all measured using what we have here as the classical bits. So you can equally perform measurements on your quantum bits. Yeah. So that is how to also perform measurements and so on and so forth. So yeah, I'll get you access to this code. You can get access to the poly Qsikit, which I can supply to you, this particular file. But then remember, you are supposed to actually apply the concepts you have learned in actually doing lab A, which is the first steps. Very, very simple. I'm sure you can just use probably about 15 minutes, 20 minutes to just finish that. If you really understood whatever we've done today, it should be something very simple for you to do. So that is it. Is there any other questions? All right, so if there are no questions, then I want to hand over to Dorcas to take over from here. Yeah, tomorrow we'll look at something different. We'll look at more of the gates and also look at quantum enigmas. I implore you to actually watch. If you go to YouTube, you type quantum enigmas, there are a lot of videos, I think about 8 of them. You just have to watch one of them. I think the link of that video will be sent to you so that you actually go to YouTube and look at the video. I think that is also present in your file. If you look at the quantum enigmas file that was given to you, that video, you've been requested to actually watch that video. Yeah, requested to watch that video. Yeah, over here. So when you click on this link, you watch the video on the quantum enigma. You don't have to watch all the series. There are a lot of videos on quantum enigmas, but just watch this particular one and before tomorrow, because the lab session is actually based on that. So tomorrow I explore more of the gates and other concepts in quantum computing to enable you easily understand and do this particular lab as well. So that is it for my end. All right, Dorcas, kindly take over.
All right, thank you so much. But before you leave, there is a question here that says that why do we take 1 over square root of 2 for the Hadamard gate instead of 1 divided by 2?
Oh, okay, so that is how to actually place something in the superposition state. It is more, like say, that is the mathematical representation of how something can be placed in a superpositional state by using 1 over root 2. If you use 1 over 2, it doesn't work out. But if you use 1 over root 2, then you can actually place that thing in a superposition state. So yes, 1 over root 2 enables something to be placed in a superpositional state.
All right, thank you. Then the other question is, just to be sure, why is there a need to measure in classical in order to collapse superposition?
Okay, usually when something is in the quantum state, what happens is that you can't actually, you don't know the state in which, let's assume we have an object A. The object A is swinging between 0 and 1 state, 0 and 1 state. You can't tell the state until you actually measure it. It's more like some kind of a pendulum bob, or let's say a coin that is spinning. When the coin is spinning, you don't know what state, whether it's head or tail that is being displayed. The only time you know whether a head or tail is displayed is when the coin has stopped spinning and then a measurement has been taken. They can now tell, oh, okay, I now see a head. Okay, I now see a tail. That is the classical state. But at the point in time where the coin was spinning, it wasn't a classical state. It was some form of like a quantum state or superpositional state. Because if I ask you to tell me, do you see a head or tail when the coin is spinning? You will tell me you don't see a head or tail because the head and tail is just spinning. It's either of those states at any point in time. The only time you can tell me you see a head is when the coin has stopped spinning. So that is what is actually happening in quantum computing. Things are in a quantum state, they are in a state of superposition. You can't actually tell the state it is at any point in time until you have measured it. When you measure it, then it collapses that quantum state and it no longer becomes a quantum state. It now becomes a classical state. So that is why you need to take measurements of quantum states. Without taking measurements, it still is in the quantum state. But as soon as you take measurement, then we have actually collapsed the quantum state and we now have a classical state. So that is the explanation.
All right, thank you so much. We don't have any more questions. So thank you so much, Dr. Nimbe. That was a very wonderful presentation. And I think we are set to go for lab 1 as we have our first step and our basics today to get lab 1 right. So we appreciate you so much for this wonderful presentation and for the lab session as well. Thank you. And to our participants, so we have shared the zip file for the Qiskit 4 first challenges in the GitHub. So kindly download it from GitHub. You can do the README to actually be familiar with which platform to use. But like I said earlier, doing it on the IBM her platform should be easier for you. So I will encourage that we get familiar with the IBM platform and do that. So you submit your lab assignments through a Google Drive folder that will provide. So I'll share that folder with you on WhatsApp and through your email as well. The deadline for submission is 11:59 p.m. GMT. That is today. So in about, it's 4 now. So in about 7 hours, you should submit your assignment. Again, Google Drive will be shared with you through WhatsApp and through your email to submit your assignment.